Is the screen visible? The shared screen?
Yes, yes.
Okay. So the main outline of this course will be, sorry, my handwriting is not so good here. First, we are going to look at some problems related to maximum matching. Basically, how to compute it, and so we are going to look at Hopcroft-Karp algorithm. And after that, we are going to see stable matching, which is basically matching. We have matching with preferences, and the preferences are on both sides. So these problems are all on bipartite graphs. So these are on bipartite graphs. And after stable matching, we are going to look into structure of stable matching and other stuffs. And then in the last part, we are going to look at matching problems with one-sided preference. So by stable matching, so what is matching problems with one-sided preference? You can think it as like there are some projects and there are some students, and we have to basically assign students to projects, and only the student have a preference over the project, but the project of course doesn't have any preference over the students. So that's like the problem with one-sided preferences. And the matching problem with two-sided preferences, one example can be there are suppose n men and n women, and each has a preference over the other gender, and now we have to basically match pair this n men pair this n men and n women to like n couples, and such that for any unmatched unmatched couple, they don't prefer each other over their current partners. So that I'll come to that. That will be our stable matching problem. So first we are going to look at look into maximum matching. Basically, we are going to see some algorithm to compute a maximal matching in an efficient way. So is the outline clear, more or less? Or if you want, you can add some topic, or you can, if you want, you can modify some topic also. I have sent you a PDF of the PDF of the plan of each week. So is the plan fine with you, or do you want to change some, or do you want to add some topic to it? Okay, I think so. We can think about it later, I guess. So first, we are going to start with maximum matching. So here we are going to generally look into. We are talking about bipartite graphs. So what is a bipartite graph? So in a bipartite graph, we call it G, and we say that the vertex set is there. And there are two disjoint vertices A and B, such that there is no edge, two independent sets. So A is an independent set and B is an independent set, and the edges are only between A and B. So it looks like this. So if it is A, so there are some vertices here, and this is B. So there is only there are only edges between A and B. So it can look like this. So feel free to ask me questions if you have any. Okay. Just one moment, I think. Hello. Okay, so we started to the new people. So we started with what we are going to with the plan. What we are going to do in this course. So first we will look into maximum matching problems, and then we are going to look into stable matching, and finally we are going to look into matching problems with one-sided preferences. So now in the first few lectures we are going to look into maximum matching problem, and so we will see some algorithms to compute. We are going to see some efficient algorithm to compute one. So we have started with bipartite graph. So what is a bipartite graph? So we can partition the vertex set in. Sorry, someone wants to join. Yeah, we can partition the vertex set into two disjoint sets A and B, such that A is an independent set and B is also an independent set, and the only edges are between A and B. So you can see in the picture below, this is a bipartite graph. Okay, and A and B are called their partitions. And what is a matching? So matching. So matching is a we will denote it as M. M is a subset of the edges E, such that each vertex has degree at most 1 in N, such that each vertex has 1 Okay, so M is called a matching if M is a subset of the edges and each vertex has at most 1 edge from M incident to it. So, and what is a maximum matching? A matching is called a maximum matching if, just one moment. Just one moment. Yeah, so a matching is called a maximum matching if, so M is a maximum matching if we take any other matching M prime, the size of M prime must be less or equal to M. So basically the matching with the most number of edges is called a maximum matching. And there is another term in terminology called maximal matching. So what is a maximal matching? M is a maximal matching if we add any more edges to M, then that set of edges will not be a matching anymore. So if for any E belongs to E minus M is not a matching. So is the definitions clear of maximum matching and the maximal matching? Hello?
Yes, sir.
And okay, you don't need to call me sir. Okay, so you can call me Pratik. It's fine. Okay, so is the definitions clear? So it's like the maximum matching is basically the so every maximum matching is maximal matching, but not every maximal matching is a maximum matching. Okay, so okay, I have also written it down here, so we can just have a quick look here. So I said like G is the set of vertices, and here I said that N is the number of vertices and M is the number of edges. So a matching M is basically a subset of the edges. So no two meet the same vertex. By that I mean that each vertex has at most one edge from M incident to it. And a matching is said to be maximal if for every edge in not in M. So this means the edge is not in M. M union E is not a matching anymore. That means there will be a vertex that will have two edges incident to it, and that means that that set of edges M union E will not be a matching anymore. And a matching is a maximum matching if there is no other matching that contains more edges than M. So this is the these are the definitions. So now our goal is, so first let's think how can we compute a maximal matching. The maximal one is the easier one. So anyone want to suggest how do we compute a maximal matching?
So I think if you just do a greedy algorithm, just take some edge and put that in the maximal matching, and then you pick some other edge which is not incident to it and put that in, and you keep going till you cannot find an edge which has the property anymore.
Yes, so that's correct. So basically we take an edge and we try to find an edge that we can put in the matching, and the set of edges in the M will still remain a matching, and if we will continue greedily do it until we cannot add any more edges. So this is an algorithm to find a maximal matching. So now to find a maximum matching, this is little bit trickier than finding a maximal matching. So for that, we are going to need to know some notations. So the first one is called alternating path. So what is an alternating path? Suppose we are given a matching M. So M is given. If we consider a path in a way that in the path the edges basically alternates between with respect to its membership in M and or not. So basically this particular edge is not in M, not in M. This one is in M. This one is not in M. And this one is in M. So if we consider a path where the edges basically alternates between its membership in M or not, in that case we call this kind of paths as an alternating path. And this vertex, if this vertex is unmatched, there is no edge incident to it that belongs to M, then we call this vertex as a free vertex. So this vertex will be called a free vertex. Sorry. Hello. Okay. So if this vertex doesn't have any edge incident to it that that belongs to M, then this vertex will be called a free vertex. And what is an augmenting path? So a path will be alternating path will be called an augmenting path if it's both of its endpoint belong to both of its endpoint are free vertices. So this and this both are free. If both of them are free vertices, then such a alternating path is called a augmenting path. So is the definition of augmenting path fine? Okay, so if it is fine, then can you tell me how can we use this augmenting path to find a bigger matching than M? Suppose we have a matching M and we have an augmenting path. Then can anybody tell me how can you use this augmenting path to get a matching that has a bigger size than M?
So you can just take out the edges which are in M and replace them by the ones which are not in M. So you get one more edge in your matching.
Yes, yeah, that is true. So we know that from the definition of the matching, that each vertex has at most one edge of the matching M incident to it. Since these two endpoints are free vertices, it doesn't have any edge from M incident to it. So when we I'll just change the color. If we match this edge and unmatch this, so okay, so we assume that this bold edges are matched edges, below the edges that belongs to M, and the light edges are the edges that are not in M. So if we change it in a way that we put this edge in M and we remove this from M, again we put this one in M, we remove this one from M, and we add this one to M, then now the property that each vertex has at most one edge from M incident to it still remains. And the good thing is, now we have one more edge from M, that the size of the matching increased by 1, because we removed 2 edges and we added 3. So the augmenting path, it is basically used to find a maximum matching. So we can use this augmenting path to find a maximum matching. So how can we find a just one moment. Just okay, so how can we use a okay, so till now we have seen that we can use this augmenting path to find a maximum matching. So now next we have one theorem, one lemma called Bird's lemma. It basically says that a matching is maximum if and only if the graph G, if and only if the graph G doesn't have any augmenting path. So what M augmenting path? So what do we mean by that? If the graph has augmenting path, then the matching is not a maximum matching, and we can increase the size of it. But the converse is also true, that if there is no M augmenting path, then the matching M is a maximum matching. So one way is easy to see, I think. So if G has a sorry, just go to next page. So if G has a augmenting path, suppose P is the augmenting path, then we have just seen that we can just change the edges that are in the matching from P. We can unmatch the edges that are matched currently matched in P, and we can match the edges that are not in M, and we can get a matching of bigger size. Okay, so this symbol is called symmetric difference. So it means that suppose we have this suppose these curly edges are the matched edges and the straight edges are the unmatched edges. By symmetric difference, we mean that the symmetric difference basically takes element an element belongs to a symmetric difference if it belongs to either in M or in P, but not in both. So that means M symmetric difference, it will also be a matching, and it will basically take this edge, this edge, this edge, and this edge, because these are the ones that are not in M. But this edge, and this edge and this edge, they belong to both M and P. That's why those edges will be removed from M symmetric difference P. Okay, and here. And when you take the symmetric difference, basically we are removing the edges that are currently matched in P from the matching, and we are adding the edges from P in P that are currently not matched. Okay, in this way we can get a bigger matching. So the next thing we have to prove that the converse is also true. What do we mean by the converse is true? It means that if here we prove that, just one moment, here we prove that if there is an augmenting path, then M is not a maximum matching. then next we will prove that if M is not a maximum matching, there will exist at least one augmenting path. Okay, so suppose M is not a maximum matching, but what does that mean? It means that there exists a matching M prime such that M prime has a strictly bigger size than M. And now if we take the symmetric difference between two matchings, then what will happen? So if let's take a symmetric difference between two matchings, then each vertex will have degree at most 2. Why so? So for each vertex, there can be at most one edge that is coming from M and one edge that is coming from M prime, but it cannot have any more edges incident to it. So for each vertex, the in the symmetric difference, we'll have a degree at most 2. Now we need to know one thing, that is, if the symmetric difference is at most 2, if the degree of a vertex is at most 2, then the structure, that structure can contain only cycles or paths. Okay, so for now, remember that each vertex in M symmetric difference M star has degree at most 2. And now we are going to look into one small lemma. It says that if a graph has if G is a graph whose maximum degree is 2, that means each vertex has at most 2 edges incident to it, then each component of that graph will be either an isolated vertex or a path or a cycle. So why is it so? So, I mean, it is intuitive. You can see that the cycles, it has every vertex has degree 2 here, and if it is a path, then the endpoints have degree 1, but the rest of the vertices have degree 2. And the third thing it can happen, it can be isolated vertex. In that case, the degree of that vertex is 0. So if you take any other structure, then what will happen? There will exist at least one vertex who will have degree more than 2. So is the proof of this lemma fine? Or any question about this? Hello? Just trying. Okay. So if you have any questions, please, you can stop me at any time and you can ask me. Okay. So from here we know that if a graph has G is a graph whose maximum degree is 2, then each component of that graph is basically either an isolated vertex or a path or a cycle. Okay. Now, if we come back to this, the proof of this lemma. So now we have seen that the symmetric difference of M and M prime has degree at most 2. That means for this particular subgraph of G, that is M symmetric difference M prime, each component will be either a cycle or a path or an isolated vertex. Okay. Now we know that we are working with a bipartite graph. That means each of its cycle is an even length cycle. So each cycle is an is of even length, because we are working with bipartite graph. And also one thing we can see that the edges in the cycle basically alternates between M and M prime. So basically it cannot happen that, suppose we have a cycle like this. It cannot happen that two consecutive edges of this cycle belong to M or M prime to a single matching, because in that case, suppose this belongs to M and this also belongs to M. In that case, this vertex will have two edges of M incident to it, which means that M will not be a matching anymore. Okay. So that means the edges in this cycle basically alternates between M and M prime. So if it belongs to M, then it will belong to M prime, M, M prime, M, M prime. So what does this mean? This means that every cycle will have the same number of edges from M than from M prime. So they will have the same number of edges. And next thing we can have, next we are going to look into paths. Okay, so the paths can be of two types. So if we see, the paths can be of either even length, either odd length or even length. Okay, so if the path, first we are going to look, see what happens if the path is of even length. So suppose there is an alternating path, suppose not alternating, suppose there is a path of even length. Okay, so again we can see that the edges of this path will alternate between its membership in M and M prime. So if it belongs to M, then it will belong to M prime. It will belong to M, M prime, M and M prime. Okay. So that means if the path is of even length, then the number of edges from M will be same as the number of edges from M prime. And now, and one more thing we know that, oh, sorry, M, not M prime, but M star that we assumed. Okay. Okay, so it's not M prime, but M star. All of that. Okay. But we have seen that the number of edges, total edges from M star is basically strictly bigger than the number of total edges from M. So what does that mean? So there will exist some component where the number of edges from M prime will be larger than the number of edges from M. So where can it happen? So it will happen in the odd length paths. So in the odd length path, suppose let's take an odd length path like this. So we have to have the property that no two consecutive edges have belong to the same M or M prime. So that means there will exist one path such that it will look like this. Where M star has one more edge than M in this path. So this must happen because the total number of edges in M star is bigger than the total number of edges in M. And if we consider this particular path, this path is basically an M augmenting path. Why is this path an M augmenting path? This is because if we consider the matching M, then this particular edge is unmatched. So I'll just write free here. And this is free. And this is also free. And this particular vertices, they are free vertices in M. This is also free vertices in M, and this is also free vertex in M. And these two edges are matched in M. So you can see that this path is basically a M augmenting path. And that basically completes our proof. That we have found an M augmenting path. And that means, so here what happened? We started with that G is not a maximum matching, and we found a M augmenting path. So that basically proves this lemma, both sided lemma. Yeah. So any question about this lemma? I mean, if you have some doubt, I can explain some part one more time.
So the last vertex is a free vertex because we chose a maximal path. Correct?
Where? Maybe you can point me out.
Yeah, the last vertex is a free vertex. When we showed that is a augmenting path.
Yes. Why it is so? Because when you are taking the symmetric difference, so you know the what is a component. Sorry, I think I missed that part. So a component is a maximal size connected graph. Okay.
Mhm.
So when we are taking this symmetric difference of m, symmetric difference m prime, each component is either a cycle or a path or a isolated vertex. So if we take an odd length path, a component is basically an odd length path. That means if there was an edge incident to it that belongs to m, then this would not be a component. So we could have extended this component and get a bigger component.
Yeah, correct. Okay, yeah, makes sense.
That means these two endpoints will be free, and that means that this is basically an m augmenting path. If you remove this m prime from here, m prime edges, and not m prime edges, if you forget about m prime and you just think about m here now, this basically makes a m augmenting path. Okay. So any more questions here? Okay, so if there is no more question, then maybe anybody want to try this corollary of this Bird's lemma? So it says that if m prime is a matching, such that m star is a matching, such that m star is size of m star is bigger than m, then if we take a symmetric difference, then it will have so basically okay, sorry, we don't need to take a symmetric difference, but if m star is bigger than m, then that graph G will contain exactly m star minus m vertex disjoint augmenting paths, m augmenting paths. Anybody want to suggest how can we solve this one? So we have to basically use this Bird's lemma. So so what do we have here? Suppose m prime equal to 6 and m equal to 3, suppose the size of m, then we say that G will have you will have 3 disjoint m augmenting paths present in the graph, vertex disjoint. So we can get it from the Bird's lemma. Okay, to solve this, what can we do? We can take m symmetric difference m star. Okay, if we take m symmetric difference m star, then each of the odd length alternating path has exactly one edge of m star. I mean, so what do we had before? We had some three type of component. So 4 type of. One is isolated vertex that we are not that doesn't help us in any way. So one, we had even length cycle where the number of edges from m is same as the number of edges from m star. One is even length path. There also number of edges from m is same as the number of edges from m star. And the third one was odd length part. So here the number of edges from m star was 1 greater than the number of edges from m. So each odd length path basically gives m star 1 more edges than m. So if the number of total edges in m star is so if the number of total edges in m star is minus the number of total edges in m is equal, the difference is equal to k. So that means there must exist k odd length path, and each of these k odd length paths and each of these paths are pairwise vertex disjoint because they basically creates a component. and each of this odd length path basically gives us a M augmenting path in G. Okay, and that's why we are going to have K vertex disjoint augmenting paths, M augmenting paths. Is the proof fine, or do you want some more explanation here? Is this one fine for you? Okay, so if this one is fine, then we can move to the next corollary of Bird's lemmas. Okay, so here what do we have? If we have a M star is a maximum matching and M be any other matching, if M is not a maximum matching, then the shortest M augmenting path has the length of shorter than this value, V divided by M star minus M minus 1. So one hint is basically I can give, we have to use this pigeonhole principle. So anybody want to attempt this problem? I mean, how to solve it? You can tell me if you got lost at some point. Hello. Hello.
So I mean, what I can think is from the previous thing, you know, that M star minus M has to be K.
Just 1 minute. I'll just share my screen. I thought my audio was not working. Okay. Yeah. So M star minus M is K.
And then you have K vertex, you have K many vertex disjoint M augmenting paths.
Yeah.
And then I don't know how to proceed from this. Let's think.
Okay. So if there are K many vertex disjoint augmenting path, what is the total number of vertices? That is the N or mod V.
Oh yeah, correct. Yeah. So there are total number of V vertices,
Yeah.
and at most, so V of them can appear in each of the paths because they are vertex disjoint.
Yeah.
So V divided by K has to.
Yeah. So we basically divide by that, and by pigeonhole principle, at least one of this. I mean, at least one of the path will have the. So basically, this is the total number of vertices, and this is the number of paths. So that means at least one of the path will have length smaller than this ratio, right? So this is basically the proof. We have to use this pigeonhole principle to solve this. Okay, so if anybody has any question till now?
Yeah. So the shortest path should have length lesser than equal to mod V by mod M star minus mod M. But why is the minus one there?
Um, so basically, the number of vertices is okay. So we can think in this way. So it's just terminology. Okay. So suppose this is an m augmenting path. Okay. So what is the number
Yeah.
of number of edges here? 1, 2, 3, 4, 5. So what are the number of vertices? Is 6. So here we say that the number of vertices in the shortest augmenting path is this v divided by m star minus n. And since the number of edges is like 1 less than that, that's why you have this minus 1. Is this fine?
Okay. Yeah. Got it.
Yeah, it's because the number of vertices in a path is 1 more than the number of edges.
Yeah.
Any other question till now? I mean, from the beginning. Sorry, it's my first class, so that's why I'm a little bit nervous. I hope you understand. So if you have any other questions from the beginning, then you can tell me. Okay, so if it is fine till now, then we can move to the next part. So how do we compute a maximum matching? So we have seen from the words lemma, it is obvious, I think. So we start with a empty matching, and then if we find a m augmenting path, then we just take the symmetric difference and we continue until we don't have any augmenting path, and then we return that matching, and then that matching will be a maximum matching. Okay. So what is our next goal then? It's what should be our next goal? Our next goal should be how can we find these augmenting paths efficiently? Okay. So we are going to give here two algorithms. One algorithm will basically find each of have the total running time of this algorithm of finding maximum matching of order n cube. Then we are going to see another faster algorithm that will have time order n to the power 2.5, 5 by 2. So we are going to see two algorithms. The first one is easy and the second one is little bit tricky. So we are going to see it, I mean, in this class or in the, and in the next class. Okay. So first let's look into order n cube algorithm. Okay. So what do we do here? Suppose we have a matching that is already been, so in this algorithm, what do we do? Our goal is to basically we start with a empty matching, and each time we find an alternating augmenting path in order n squared time, and then we augment it and we continue until we don't have any more augmenting path. So that's why the total running time is n cube. So how do we find an augmenting path? So suppose we have a graph G where suppose on 3 vertices, and the red edges are the matched edges and the blue edges are the unmatched edges. Okay, so suppose this is the graph. Now what we do is that we convert this graph to a directed graph. And how do we do it? We add an arrow from left to right if the edge is unmatched. And we add an arrow from right to left if the edge is matched. Just 1 minute, I'll just draw it a little bit bigger. It will be clearer. Okay. So suppose these are the vertices. And suppose there are some unmatched edges. Okay, suppose the red edges are the matched edges and the blue edges are the unmatched edges. Okay, so now what we do, we basically add an arrow from left to right. We direct the edge from left to right if that edge is unmatched, suppose like this. And we direct the edge from right to left if the edge is matched. So suppose this. Now what we do, suppose this A0 is the free vertices on the left hand side. And B0 free vertices on the right. Okay, so now what we do is we basically use a search algorithm from each of the free vertices on the left, and we see that if we can reach the some vertex on the right which is also free. So for example, we can start our searching from here, this vertex, and we can go this direction, and then we can see that we have a we can come in this direction, and then if we go to this direction, then we can see that we have reached a free vertex of B, which is in B0. So and then this particular path will be a augmenting path. So is the construction clear? Okay, so if the construction is fine, then we can come back here to the algorithm. So basically what we are doing here, we are constructing this directed graph from the H from G. So here what we are doing, we are adding the edges are directed from B to A, as we have shown here. From suppose this is the A side and this is the B side. So the edges are directed from B to A if it belongs to M, and we are if it doesn't belong to M, then we direct it from A to B. And suppose A0 and B0 are the free vertices of A and B. So that's what we have defined here. Okay, now we use a DFS algorithm, searching algorithm for from each vertex of A0 and stop as soon as we reach a vertex in B0. And that path will be basically a M augmenting path in G. And the searching algorithm will basically take order M time, which is like order n square, each time to find a augmenting path. And the total number of iterations will be n, because the size of the maximum matching can be at most the number of vertices. N. So number of total vertices divided by 2. So that means the total running time of this algorithm will be order n cube. Okay, so is there any question about this?
So you repeat this till there are no more free vertices left, or so I don't get when you stop the algorithm. Like
So
you do it once and you
So we basically stop the algorithm if we can't find such a path, the path I have shown here. So what is happening here? After we find such an augmenting path, so okay. So what we are doing, we are constructing this H graph, directed graph H from G, and then we are trying to find a path in H from A0 to B0. If we can find such a path, then we say that that path will be a augmenting path. And if we can't find such a path, then we say that there doesn't exist any augmenting path in the graph, and that means the current matching is a maximum matching, and that time we stop.
okay. Thank you. Yeah, I see it.
So can you see why it is so that when there is no directed path from A0 to B0, then that there will not exist an augmenting path? I mean, is it clear to you why it is happening?
So because it's bipartite, when you go on a blue arrow, the next one should be red, if you have such a path.
Mhm.
And yeah, so suppose there was an augmenting path, then it would have to start on a free vertex and end on a free vertex, and you would always follow the directions which you assigned. And so
Yes.
you would find this path in the.
Yes. So basically, if there is an augmenting path, so it will have one endpoint in A0, and we basically start from A0 and do a searching algorithm. So we will always find that and find that path, because the augmenting path basically alternates between unmatched and matched edges, and we can see that if we suppose this is the first free vertex, then we can see that the first unmatched edge will be a blue edge from A to B, and then the next matched edge will be from B to A, and it will go as long as we reach some vertex in B0. And here it will happen because the other endpoint will be, if one endpoint of that augmenting path is in A0, then the other endpoint of that augmenting path will be in B0. Yeah, so that's why we'll find. So is it clear to everyone else, the order n-cube algorithm? Because the next one will be a little bit complicated, so that's why I'm asking.
So each time you do the DF, it takes O of n, correct?
Often, okay. So one thing is that this is a good question. So if we do the DFS from each of the vertices separately, each of the vertices of A0 separately, then it will take a way longer time, right? Because each time it will take order n time.
Yes.
But what we do instead of that, we create a super vertex, suppose A0, and we add an edge to each of the free vertices of A. Now, if we do the DFS, then it will take order m time, right? Because now we are doing only one DFS.
Yes.
So we basically add a super vertex on the left hand side and also add a super vertex on the right hand side, and add the edges to all the free vertices from A0 to all the free vertices of A, and from B to all the free vertices of B to B0. We add these two edges, and then we run the DFS. And now it will be order n time, because you run only one DFS now. Okay. So now if it is fine, then we can move to the, I think, let me just check that. So, okay, so I have some one more small lemma. So you know the relation between maximal and maximum matching. So we have seen the definitions of maximal and maximum. So any maximal size of any maximal matching will be at least half of the size of the maximum matching. So do you know the proof of this lemma? So you can try to solve, try to do it at home, and maybe we can discuss this on the next class. Will this be fine? Okay, so we can keep this for home maybe. So the problem is that any maximal matching will have size at least half of the size of the maximum match, its maximum matching. Okay. So on the next class, we can try to check. I mean,